Welcome friends, let's talk a little about Wronskian. So begin with the matrix M of t, and then within here, put brackets, and then put an e to the t, e to the 2t, these are just made up functions, differentiate e to the t, which is just e to the t, and then differentiate e to the t, which is by the chain rule 2e to the 2t. Let's just, for example, find this at like t equals 0. This is a function of time. Notice each entry has t as a variable. That means each entry can be evaluated at t equals a number. So let's say is 0. So e to the 0 is 1. E to the 2 times 0 is e to the 0, which is 1. E to the 0 is 1. And then this is 2. Okay, because e to the 2 times 0 is e to the 0, which is 1. 1 times 2 is 2. Notice that at this instant in time, at t equals 0, then we have just a matrix. In other words, this is like a vector, and call this v sub 2. This is just another vector, you see? So that means we can graph them in the coordinate system. Let's do that over here. Let me just enable the grid line so I can see things better. Okay, so let's see. Let's mark 1, 1. So that means 1 to the right. I'm going to call that two boxes, 1 up. The other one is 1, 2, so make that red. So that's going to be 1 to the right and then 2 up. And notice something happens in this particular case. Let me freeze this 1 sec. If I make a copy of the green one and I place it here, I make a copy of the red one and I place it here, then what we see happening is that there's an area that is spanned, right? And specifically, this area is definitely not equal to 0. It's some positive value. Okay. Notice further that in this case, right, if this is the vector v1 and this is the vector v2, that these vectors point in different directions. Not really in opposite directions, but at least in different directions. So at this instant in time, we have essentially a parallelogram kind of shape, and it has some area not equal to 0. Okay, whatever. You go to Home Depot, get some paint, and you paint the area inside it. Okay, so now, in general, how does this work? Well, we just defined the Wronskian along, or based on the kind of similar reasoning, okay? So then you're going to do e to the t, and then e to the 2t, and then here e to the t, and then the derivative of the second one, which is 2e to the 2t. To find the area inside the shape, when we have specific columns like 1, 1, and 1, 2, what would we do? Well, we would do the determinant of, say, m of 0 like this, okay? So that means specifically you just do 1 times 2 minus 1 times 1 like this. So geometrically, this is just 2 minus 1, which is 1. This tells you that the area that the shape contains is 1 unit. You can extend this even to this case, where you have functions input. So we're going to have the following: e to the t times 2e to the 2t, doesn't really matter, and then e to the t, and then e to the 2t, and then you work through this, so it's e to the 3t with the 2 on the outside, you add up the exponents, and then e to the t plus 2t is 3t, so it's minus e to the 3t, therefore we end up with e to the 3t. Notice something important, right? This is just a function of t, isn't it? This function of t in this particular case, e to the 3t, this is never equal to 0. Okay, so let me just show you a graph that might be somewhat helpful here. Let me relate an important piece of information. But before I do that, let me just quickly zoom in on a small window on the origin like this. Okay, now let's graph e to the 3t. This is just the Wronskian. So look at what's happening here in this graph. When t has the value 0, then w of 0 is equal to 1, which is what's plotted on the vertical axis right here. You see this? When t is 0, then w of 0 is equal to 1. So you relate that to the graph that I drew first, because this one is just the area enclosed by the vectors. That's all. Okay? Then the question is, how does any of this help us understand whether e to the t, and then e to the 2t, whether these are linearly dependent or linearly independent? Well, look, at t equals 0, v1 points this way, v2 points this way. There's an area that's spanned by them. But the point is that they're pointing in different directions, aren't they? Okay, so it's important to understand. They're pointing in different directions. They're not linearly dependent at t equals 0. Because overall, as you can see from this graph, as t, say, increases towards positive infinity, see, this kind of goes up forever. That means the area is never equal to 0. If the area is never equal to 0, the only way that can happen is if that e to the t and then e to the 2t are linearly independent this way, okay? If they were linearly dependent, then you might have, for example, vectors point in the same direction, and then the area would be equal to 0, you see? In this case, as you can see, e to the 3t is never equal to 0. That essentially represents the area spanned by the vectors. And the implication that it tells us about is that the vectors always point in different directions. They're never linearly dependent. That means, in other words, the functions e to the t and e to the t are linearly independent. Look at the difference if you do this. M of t is equal to, okay, make up a matrix. T 2t, derivative of t is 1, derivative of 2t is 2. So look at the difference here. This is not the same thing anymore. Like m of 0, look what happens. You're going to have 0, 0, just plug in t equals 0, 1 and 2. So if you graph these in a coordinate system, again, this is just a snapshot in time at t equals 0. So it's just a pair of vectors at t equals 0. You have to imagine infinitely many other vectors. Oh, going back here, by the way. Again, let me stress, right? Like, this is just v1 and v2 are just two vectors at t equals 0, but you have to really imagine that this object evolves over time, and that means that the area enclosed by the vectors evolves over time, and the value of it is what you see represented in this graph, okay, over time, from a kind of geometric perspective. But again, the implication is that the vectors that represented by e to the t, and e to the 2t, and 2e to the 2t, those vectors are linearly independent. They're not multiples of each other. So now let's graph this. Okay, make a coordinate system, add some grid lines. Okay, now let's do some of the following. 0, 1. So that means 0 along x, 1 along y. So it's like two boxes. If you make that one unit, see, I forgot to switch over to 1 second. I need to grab the arrow like this. Okay, and then 0, 2 again. Notice it points in the same direction, but it's just twice as long. But the point is that you see these vectors at just one instant in time, they're linearly dependent clearly, right? They're just multiples of each other. So in other words, if you call v sub 2, 0, 2, then that's just 2 times v sub 1. That's all. If you wanted to, you could do it this way. You could go, okay, 0, 2 is really like, I could write it's 2 times 0, and then 2 times 1. Okay, but that's just 2 on the outside, and what's left is 0 and then 1. So you see, it's double 0, 1. Let's also do the Wronskian then as 0, so... Okay, it's, let's see, 0, 0, 1, and 2. So apply it. It's 0 times 2 minus 1 times 0, but that's 0 minus 0, which is 0. That's not surprising because, as you can see, if the vectors are linearly dependent, there's no area enclosed between them. Okay, and then in general here, as a function of time, if you were to repeat the same logic, essentially, what would you have? You would have t, 2t, 1, and 2. Alright, and then kind of enclose this, so you're going to have 2t minus 1 times 2t, essentially, you see? Which is just 0 again. So for any t, this is equal to 0. That means that, in other words, the conclusion is this one, that t and 2t are linearly dependent functions. That's what it allows you to conclude. Okay, let's leave it at that. So leave a like if it's been helpful, friends.